Hello everyone. Welcome to the TCS seminar at Jagiellonian University. Today our guest is Jim Geelen, who is very well known from his work on matroid theory, in particular on the extension of graph minor projects to matroids. He won the Fulkerson Prize. He won the Coxeter-James Prize of the Canadian Mathematical Society. And today he will tell us about average plane size, which I think also has some connections to matroids.
Yes, thank you very much for the introduction and for the invitation. So this is some work that I'm pretty excited about. It's joint work with my PhD student, Matthew Croker, and my former student, Rutger Campbell, who now works with Sung-Along in Korea. So it's basically a question in classical geometry. And I really like it because it's one of my few theorems that I can basically tell to anybody. I could go up to a person in the street and just tell them what the theorem says. And I have indeed done that. I've my climbing gym, I've told people I've been climbing with, I was excited I proved this theorem, so I told them the theorem. And I believe they understood the statement of the theorem. It was pretty clear they didn't know why I cared. And they certainly didn't care, but I think they understood the statement of the theorem. So there's not many results that I prove where I can do that. So let me jump into the predecessor results. So this is based on a theorem. So our work is a generalizable, an extension of a theorem of Melchior's from 1941. Melchior's theorem says that if I take a finite collection of points in the plane, not all on one line, then the average length of a spanned line is less than 3. So there's just a couple of things in quotes there that I need to clarify. So the spanned lines are the lines that go through 2 of the given points. Right, so that's my spanned lines. And when I talk about the length of a spanned line, I'm talking about the number of the given points on that line. So the blue lines there have length 3 and the red lines have length 2. Melchior's theorem says, however I do this, I mean, if I just put a set of points in the plane, as long as they're not on a line, the average length of the lines, the spanned lines, is going to be less than 3. So it's a very pretty theorem. It's also got an incredibly pretty proof, which I'm going to just quickly skim through now. It's not actually related to anything else that I'm doing in the talk, but the proof is so nice that it would be a crime not to explain it. So the first thing is I'm thinking about a finite set of points in the plane, and I may as well be thinking about the projective plane because I can always put the line in at infinity, it doesn't matter. And now I'm going to make use of the duality, the projective duality between points and lines. So I've got those 7 yellow points now turn into 7 lines. And if I've got a line with 3 points on it, that's going to become a point that's the intersection of 3 of the yellow lines. So the blue lines there on the left turn into blue points on the right, which are the intersection of 3 lines. So now I've got this line arrangement, and I'm interested in the multiplicities of the intersection points. The condition that the points aren't all in one line originally turns into the lines not being copunctual. And the result is that the average multiplicity of the intersection points is less than 3. And in fact, this was the theorem that Melchior proved, essentially. And he stated his result in terms of line arrangements. You can go from the plane, you can project, you basically have a stereographic projection, you can just project onto a sphere. So lines turn into great circles when you do that. And points, each point in the plane turns into a pair of antipodal points on the sphere. And so another way to say the same result is that if you take a collection of great circles on the sphere, and then it can't all just go through the north and south pole, right? I mean, I'm not interested in that. That's not going to work for me. So as long as they're not like that, then the average multiplicity of an intersection point is going to be less than 3. This is actually quite obviously true, easy to see, because if you look at there's clearly a graph sitting there, a planar graph sitting on the sphere. And the intersection points, the multiplicity of an intersection point is half its degree. And planar graphs have average degree less than 6. So that's really pretty. Okay. So on to our results. So we wanted to extend this, and it's kind of natural. I don't really fully understand why this isn't already a theorem in the literature, but it seems not to be. So you take, so we start off in Melchior's theorem, we start off with a finite set of points in the plane, so it's natural to consider a finite set of points in R3. And now I look at the spanned plane. So these are planes given by 3 non-collinear points in the set. And I'll talk about the size of a plane just to be the number of points from a given set on the plane. And I want to say that the average plane size is bounded above by a constant. In Melchior's result, we needed that all of the points weren't on one line, and so clearly we need that all the points aren't on a given plane. So that's sort of the first thing you might hope is true, but it's not quite true, because there's one other issue, that it can be that all of the points lie in the union of 2 lines. That's problematic because every spanned plane here contains one of those 2 lines. So if those lines were very long, every plane would be large, and of course the average would be large. So I can make the average plane size in these kinds of pictures, I can make the average plane size arbitrarily large. But that's the theorem. The theorem is that if you take a finite collection of points in the plane and it doesn't have one of these 2 degenerate configurations, so I don't have all of them in one plane and I don't have them all on 2 lines, then the average plane size is bounded above by an absolute constant. Okay, so that's the main theorem. And I imagine that most of you are probably wondering a little bit about that absolute constant. In Melchior's result, there was this nice number 3. We don't actually know much about this constant. And the reason for that is that we rely on results from other papers where they just implicitly talk about constants. They don't say exactly what they are. If you trace back through the papers, everything is clearly computable. It's just laziness on our behalf that we haven't gone through and computed a number. If we did compute a number, it would be pretty bad. I'd be a bit surprised if it was less than 1,000, for example, the bound we sort of get just from the machinery without doing any optimization. I'm pretty sure you could optimize it to get less than 1,000. The truth is probably a single-digit number. So I think that's an interesting question. What is the right number there? One other thing I want to mention about the result is that this R3 can actually be arbitrary. Like if I look at plane size in arbitrary dimension, this is plane size, not hyperplane size. You can put any dimension there. And the reason for that is that you can project down to R3. So I can take a collection of points in higher dimensional space. I can fix some hyperplane in general position and project orthogonally onto that hyperplane. And when you do that, the planes stay the same. The set of points that are coplanar stay the same. And so you can project all the way down to R3. And the same thing happens in Melchior's result. So Melchior's result was talking about the plane, but you could look at lines in arbitrary dimension and you get the same result. As soon as you sort of get these questions, you can just project down to the right space so that the objects you're interested in are hyperplanes in that space. Okay, we're not going to really make use of that, but I thought I would mention that fact. Okay. So that's basically the introduction. And so now let me just give you a brief overview of where we're going. I'm going to introduce matroid terminology, probably more out of laziness than anything. I'm a matroid theorist and I think about things using matroid terminology. I'm not doing any matroid theory in this talk. I just find the language of matroids convenient to talk about combinatorial geometry. And there's a natural reason for that. I mean, matroids themselves are combinatorial abstractions from linear algebra. And so everything naturally sort of sits naturally in the language of matroid theory when you're doing combinatorial geometry. So there won't be, I mean, you don't be scared off. It's just a change of language a little bit. So after I do that, I'm going to give you a second proof of Melchior's theorem. And this one is going to be a lot more instructive in terms of what we do. It's possible that there's a proof of our result using something like Melchior's original proof. There is this Euler-Poincaré formula that should help in higher dimensions, but we don't know how to do that at this stage. And that's sort of interesting because maybe that approach might lead to better constants, like really good constants. But at the moment, we don't know how to do that. So we use quite a different approach. And so I'll explain that approach in a fair bit of detail for lines. So by proving this generalization of, or by reproving Melchior's theorem using Beck's theorem. And then I'll spend a while explaining how Beck's theorem generalizes to higher dimensional flats, mostly focusing on planes. And then finally, we'll talk about our results and some related open problems. The open problems are mostly going to be just talking about what we think the constants might be in some of these results. Okay. So what's this matroid terminology? So I want to think about these points from a combinatorial perspective. I really don't care about the specific coordinatization. I want to think about just the combinatorial dependencies, and matroids do that nicely. So instead of taking a finite subset of R to the D, I'm going to take a finite set, think of them as labels, and I'm going to take a map injectively into R to the D. So I'm just putting some labels on points in R to the D. And then I'm going to remember which subsets are affinely independent and which are not. So that's all of the combinatorial information about the embedding. Right, so some sets are affinely independent, some are not affinely independent, and that tells me everything I need to know combinatorially about the embedding. I don't care about the actual coordinates. And after that, I can define a rank function. So I can define the rank of a set. So you take a subset X of E, I can define its rank to be the size of the largest independent subset, or affinely independent subset of it. So in other words, I could take the set X and I could look at the affine subspace that it spans and take its dimension, and the rank of X minus 1 is that dimension. So points have dimension 0, but rank 1. So there's this off by 1 thing when you go to matroids. And just a brief comment for people who are familiar with matroids is that because of the way I've done this construction, we've taken this injective map of the points into R to the D. I don't get pairs of elements with rank 1. Right? My elements each have rank 1, my pairs each have rank 2. They're distinct. And matroids of that kind are called simple. So you'll see the word simple all over the place, and it's just related to the fact that this map's injective. Okay, so the objects we care about are the flats. So a rank K flat is an inclusion-wise maximal set with rank K. So the points are the rank 1 flats, the lines are the rank 2 flats, the planes are the rank 3 flats, etc. So for example, in the right here, the set ABC is a rank 2 flat, so it's a line. But the nice thing is, it's not this geometric line in space. It's the combinatorial part of the line that I care about. So when we talk about lines in matroids, we're just getting the combinatorial information that we care about from the line, the set of the given points on the line. And so these are the things that I'm trying to find the average of. I'm trying to find the average line size. It's really the size, the average of the sizes of these sets. So the lines are precisely the span line, like the points on the span line. So it's getting precisely to the combinatorial information we like. And so now we can, in this terminology, rewrite our results. So Melchior's theorem, for example, says that in a simple rank 3 real representable matroid, the average line length is less than 3. If you notice in Melchior's theorem itself, there's this thing that says not all on one line. But because I'm saying it's a simple rank 3 matroid, it precludes the possibility that they're all on one line, because that would be a rank 2 matroid, right? So you can, it slightly simplifies the statements. And our main theorem in matroid theoretic terminology says that if you have a simple rank 4 real representable matroid, the average plane size is bounded above by an absolute constant unless the matroid is the union of 2 lines. Okay. But just a brief word about notation. If I'm being a bit sloppy at times, I might talk about M, and I mean a simple n-element real representable matroid with rank at least 3. And I'll be using the following notation. Script L is the set of lines, script P is the set of planes, script F sub K is the set of rank K flats, and script F is the set of flats. You don't really need to commit that to memory because I'll tend to remind you as we go along what these things mean. Okay. So I'm going to start by giving you this second proof of Melchior's theorem. So I've got a simple rank 3 real representable matroid. I want to show the average line length is bounded above by some absolute constant. I'm not going to worry too much about what that constant is. I'm just going to give you some bound. If you're careful, you can get 6, I think, from this technique. And we're just going to do the obvious thing. I'm going to look at the average line length. I just take the sum of the line lengths divided by the number of lines. So I need to get an upper bound on the sum of the line lengths and a lower bound on the number of lines. One thing to bear in mind is I'm after an upper bound on the average line length that's a constant. And that means that my estimate on the number of lines had better be correct within a multiplicative constant, otherwise I'm in trouble. Okay, if I'm not estimating the number of lines well, I'm not going to be able to get a constant bound on the average line length by this technique. So that's a really key difficulty, but fortunately, it was solved by other people. So there's been quite a lot of work in the literature around computing average line length, and also not average line length, sorry, the number of lines, and also for the number of planes and the number of flats of other rank. So the first observation in this direction is that the number of lines is at most n squared, the number of points squared, because every pair of points spans a line. So the first thing you might wonder is, when is the number of lines of that order of magnitude? When is the number of lines in the some constant times n squared? And there's this beautiful theorem of Beck's that says that you either have the number of lines close to n squared, or one of your lines is really long, which is a bit of a surprising theorem. And in fact, Beck's theorem is slightly stronger than this. This is just a, so I've got some special specific numbers here. So you can replace this 0.9 by 1 minus epsilon. And then this 1 over 12 becomes a delta. So you can basically, if the number of lines is far from n squared, then the length of the longest line gets really close to n, the number of points. So nearly all points are on one line. Okay, but this doesn't quite give us what we want, right? We need to count. We need to count the number of lines in all cases. So we also need to deal with the case that there is a very long line. And this was actually done by Lund, and it's an easy corollary of Beck's theorem. So the number of lines, it turns out, is pretty close to n times n minus g2, where g2 is the length of the longest line. Now, this is an obvious upper bound on the number of lines, because if you take 2 points, I don't want them to both come from the longest line, because that's like all pairs of points in the longest line just give me the longest line back again. So there's only one line I get that way. So I need to choose at least one of the points off of the longest line. So clearly you get an upper bound of n times n minus g2 plus 1 on the number of lines. The plus 1 being for the longest line itself. And the reason you get the lower bound is you look at Beck's theorem, and there's these two cases. Either the number of lines is at least a 12th n squared, which is, of course, larger than 12th n times n minus g2. Or your longest line is really long. And now what I'm going to do is I'm going to look at points off the line. There's only a few of those, but I look at points. You see my cursor? I think you do by memory. So the number of choices for this yellow point here is n minus g2. And I look at the lines that go through this yellow point and one of these blue points down here. Some of them will contain other yellow points, so there'd be double counting. But not too many, because there's only 0.1 times n yellow points at most. And there's 0.9 times n blue points. So 0.8 times n of these will make 2-point lines. So if I fix this point here and I look at the different choices of blue point down here, 0.8 times n of those points down there will just define a 2-point line. So if I just count the 2-point lines here, I get a bound of the lower bound of the right order of magnitude. Okay. Is that clear? Okay. So now we have a good estimate on the number of lines. And so to finish the result off, we need to get an upper bound on the sum of line lengths of the same form. And we get that upper bound using this result. This is slightly different, right? I mean, here I just have the size of L and I'm summing up over all lines. In this result, I got the size of L minus 4, and I'm not looking at the longest line. I'm looking at all lines except the longest line. Now, there's a couple of observations. This minus 4 is nothing, right? I mean, I'm trying to get an average. If I'm trying to get the average, subtracting 4 is only going to change it by a constant. So I can forget about that minus 4. That's sort of unimportant. It only shifts the average by 4. Dropping the longest line is not much of a drama, because the number of lines is more than the length of the longest line, because I can just fix a point out here, and then for every point out here, every yellow point, I get a line through that point and one of the blue points. So the number of lines is more than the length of the longest line. So the longest line can contribute at most 1 to the average. Right, so if I've proved this result here, that gives me the bound. That gives me what I want. Is that clear? Okay. So I'm going to define this set T, script T, which is the set of all ordered pairs where I choose one element arbitrarily from the matroid, and then I choose a second element not from D, and the only other condition is that these pairs are distinct. So the number of these pairs is roughly n times n minus g2. Right? So n choices for E, and then around n minus g2 choices for F. And so I'm going to prove that bound instead. Okay. So the thing about this, so script T, these pairs, these ordered pairs in script T, they each span lines that I care about. And all I need to prove is that every line that I care about contributes at least the size of L minus 4 distinct pairs to script T. So let's take a line other than D and ask how many distinct pairs it determines in script T. So I get to choose 2 points, distinct points, and the second one can't be in D. The line L and the line D intersect in at most 1 point. So what I'm going to do is I'm going to choose F first. And the number of choices for F is the size of L minus 1. And then I choose E, and E can be any point other than F. So that's another L minus 1 factor. And then you get this nice calculation here, which says that that's at least 12 times the size of L minus 4. And then that gives you precisely the inequality we wanted. Okay. So that gives us the proof of Melchior's theorem. There were 2 interesting 12s that occurred in the proof that basically end up cancelling each other out. So there's 4, and then the 1 for what extra 1 you get for D ends up giving you a bound, I think, of 6. In the theorem if you go through it. Okay. So I'm not going to go through a lot of the details for planes. I'll just sort of talk about the shape of the proof of planes. But it really follows very closely what happened for lines. So if I want to compute average plane size, the first thing we need is a very good estimate on the number of planes. So what we used for that in the case of Melchior's result was Beck's theorem and this corollary. Beck's theorem. So Beck's theorem says that either the number of lines is roughly n squared, or the length of the line, the longest line, is roughly n. So we need something like that for planes. And then we really want this result that counts the number of planes up to some multiplicative constant, correct, up to some multiplicative constant. And there is a theorem for this, like Beck's theorem. And obviously the bound on the number of planes is n cubed, because you're choosing 3 points. So either the number of planes is in the order of n cubed, or something's close to n. What is that something? So in the case of Melchior's result, we cared about lines, which I can just think about as sets of rank at most 2. So I define a 2 degenerate set to be a set of rank at most 2, and so the size of the largest 2 degenerate set is going to be a line. That's going to be the longest line. And this is, so the 2 degenerate sets are exactly the sets that Melchior's theorem, exactly the sets that Melchior's theorem doesn't say anything about, right? So Melchior's theorem says that the rank is going to be at least 3. So these are the sets that Melchior's theorem doesn't say anything about. And in the case of planes, the sets that we don't say anything about are the ones that are either the rank is at most 3, or they're the union of two lines. So I'll call a set 3 degenerate if it's got that form. So another way to say our result is that if I have a 3 degenerate matroid, the average plane size is going to be a non-3 degenerate matroid, the average plane size is bounded. So, so now Doe's theorem says that either the number of planes is in the order of n cubed, or the size of the largest 3 degenerate set is close to n. And again, I haven't stated this really precisely, but there's an epsilon and a delta that you can throw in there and make it precise. But that's sort of the gist of Doe's theorem. And then we prove as a corollary of that the number of planes is in the order of n times n minus g2 times n minus g3. So that's n times n minus the length of the longest line times n minus the size of the largest 3 degenerate set. So again, you can easily show that this is going to be an upper bound. And the main work is showing the lower bound, but if you use Doe's theorem, it's a half-page proof. Oops. So Lund had actually proved a similar result to this, but he had a condition on, so this says that G3, so this saying that M is not 3 degenerate, it says that N is strictly larger than G3, right? So N minus G3 is positive. Lund had a condition that said that N minus G3 had to be at least some absolute constant that he didn't specifically determine. So there was that difference there, and we just got that constant. We just showed that constant didn't play a role in case of planes. Okay, so that's great. We now know the number of planes really accurately. Like we have a very precise count on the number of planes in a real representable matroid, which is a bit of a surprising result in itself. So Doe actually proved a very general theorem. She showed something similar for rank K flats, not just planes, but for rank K flats, she showed that, well, that P shouldn't be the number of planes. It should be the number of rank K flats. Sorry about that. So in a simple real representable matroid, either the number of rank K flats is in the order of n to the k, or the size of the largest K degenerate set is really close to n. So what's a K degenerate set? So this is a concept that arose in Doe and Lund's work independently, but there's also something similar very similar in a paper of Lovaas's from the 70s, and he was talking about rigidity of bar and frame, bar and joint frameworks. Anyway, so a set's K degenerate if its rank is at most K, or you can partition the set into a collection of sets x1 up to xt, each of rank at least 2, such that the sum of the ranks minus 1 is less than K. And it's a weird definition when you first come across it. So first of all, if you take two lines and you think about what's going on here, if you take two lines, you just get 2 on the left, so that's 3 degenerate. So 2 lines gives you something 3 degenerate. So let's suppose you've got this partition. So let's suppose I give you this partition. What can we say about it? Well, the first thing you can say about it is that T has to be less than K. So each of these terms here, because these sets each have rank at least 2, each of these terms is at least 1. So T has to be less than K. So there's not too many sets. So if you think of K as being a fixed constant here, I don't have too many sets. And the next observation is that every rank K flat has to contain one of these sets. And the way to see that is you take a set of affinely independent K affinely independent points in your flat. If it doesn't span any of these sets, if it doesn't span X1, for example, it can contain at most the rank of X1 minus 1 points from that basis, from that affinely independent set. And then the pigeonhole principle just gives you a contradiction. Right, there's K points and this sum is less than K, so one of those sets has to contain the rank of that set number of different points, and then that flat will span that set. Okay, it's just pigeonhole principle that every rank K flat of the matroid has to contain one of the sets. And that tells you, these two conditions 1 and 2 tell you that the number of rank K flats is significantly less than the bound of n to the K. It's actually n to the K minus 2, because if I think about the number of flats that contain X1, it's got rank at least 2, so I only get to choose. So if it had rank 2, for example, I only get to choose to choose the rest of the flat. I only get to choose K minus 2 points outside to span it. And there's not very many of these flats. If you think of K as a fixed constant, the number of flats is a constant, and so you get this result. Right, so you have significantly, if you have this degeneracy, you get a lot fewer flats than you expect. And the other observation is that degeneracy is problematic for average flat size because of this second condition. If all of these sets X1 up to XT were large, then the average size of a rank K flat would be large. And over the reals, I can make them large just by adding points freely to the spans of those sets. You just throw a whole bunch of points into X1 and a whole bunch of points into X2. I can once I got an example with some degeneracy, I can make lots of other examples with the same sort of degeneracy, but where the average size of a rank K flat is huge. So degeneracy is a very natural condition. If you're interested in either counting rank K flats or if you're interested in the average size of rank K flats. Okay, so Lund proved. So we already saw Doe's theorem. So Doe's theorem says that it's basically the natural analog of Beck's theorem said that either the number of rank K flats is in the order of n to the K, or the size of the largest K degenerate set is really close to n. Right, so that generalizes Beck's theorem in the best possible way. Lund proved that the number of rank K flats is in the order of n times n minus g2 up to n minus gk, unless your matroid is very close to being K degenerate. So you can just delete a constant number of elements from your matroid and become K degenerate. Okay. So that's weaker than what we would like. I mean, we would like to just say that this is true unless the matroid's K degenerate, and life would be great. But we have this. It's close, but not quite there. So what we did is prove the following result, that the sum of the flat sizes, if M is not K degenerate, so here we actually get a really nice result, right? If M, this simply says that M is not K degenerate, so I don't have this other condition about not being nearly K degenerate. If it's not K degenerate, then the sum of the flat sizes is of this order of magnitude. And that's the same form as Lund's theorem for the number of rank K flats. And so that gives you this constant average when this theorem applies. But this theorem doesn't always apply. So let me give you a brief sketch as to how the proof goes. I mean, it just works like we did for lines. So you let DI denote the size of the largest I-degenerate set. And now I look at all tuples, E1 up to EK, where E1 is chosen arbitrarily, E2 is not in the 2-degenerate set, and EK is not in the K-degenerate set. And in addition to that, I'm only going to look at tuples that actually span rank K flats. And now I think about the set of flats that they span. So these tuples span some collection of flats. In the case of the lines, the only flat we didn't get was the actual longest line itself. Here, that's not true. So there will be other flats you don't get, but they're sort of degenerate in a certain way. There's actually very few of them, but they're quite possibly very large. So they're incredibly few, and that is related to this third observation here, that when the flats that you're not counting by these tuples tend to be very few, but unfortunately they can be really big because they contain one of these sets from the degenerate thing. So they can be sort of roughly in the order of n, but there's very few of them. It turns out that dealing with these degenerate flats is the bulk of the difficulty, unlike the case for lines. As for the other flats, all you need to do is to show that if I take one of the flats that is spanned by one of these tuples, then that flat spans enough distinct tuples in T. And this is very straightforward. This is no more difficult than it was for lines. You basically just, this is just using basis exchange. It's a 2-sentence argument. You fix one basis and then every other element can be exchanged into the basis. You get a lot of bases and every basis has an ordering. And effectively, it's all you need. So that's roughly why the theorem is true. It's not, so this theorem for the most part isn't a lot more complicated than the argument for lines. The argument for the lines can be written in a short paragraph. This can be written in a page, and the page is mostly dealing with these weird flats that aren't counted by the tuples. Okay, so now that we've got that theorem, at least for planes, we're now done. We now know from this result and the earlier result about the number of planes, we get our main theorem. Okay. But then for rank K flats, so if we want to go past rank K, if we want to go past planes, this condition is really annoying. I mean, I could easily write down a theorem that says that if that condition is true, so if you're far from being degenerate, then I can tell you the average is at most a constant. But it'd be really nice to just have a better theorem. We don't have an understanding of the mechanism that determines when the average size of a rank K flat is a constant. We just don't understand it, and it's because we don't know how to count rank K flats when you're in a matroid that's too close to being degenerate. And partly it's maybe because we're too stupid, but it's also partly because it's also just there is a difficulty. I mean, you can't just replace that condition by M not being K degenerate. So here is an example when K is 5. I'm not going to go into the construction and explain why it's true, but for K equals 5, you can't just write the same result with M not being K degenerate. Okay. And that's annoying. I'd really like to understand that better. I would really like to be able to count the number of rank K flats better than that and have an understanding about what the real structure is or what the right answer is when you're close to being degenerate. I'd like to understand that. There is a nice way you can get to a general result that changes our main theorem. So there's a different way to state our theorem, and that is, our theorem is equivalent to the statement that in a simple rank for real representable matroid, the average size of a flat is bounded above by an absolute constant. So our theorem is talking about planes, but here I just talk about arbitrary flats and I don't specify the rank of the flat. So here I'll be looking at the empty flat, the points, the lines, the planes, and the matroid itself. I look at all of the flats. And the average size there is bounded. And the way you can see that is that, well, our result says that the planes, you get a bound for planes, well, except in some exceptional case that you have to think about explicitly. So our result gives it for planes, Melchior's result gives it for lines. And then if you throw together the whole, the flat consisting of all points in the matroid, together with all of the points, you get a bound of 2 for the union of those things, right? There's one really big flat and I get one flat with size n and n flats with size 1. And then there's one flat with size 0. So you get this result that says that if you just take the average flat size, it's bounded above by an absolute constant. And this theorem is nice because it doesn't have any conditions, right? I mean, there's this unless m is the union of 2 lines, and that disappears because you can just compute the average in this case and see that it works. And that result actually extends to arbitrary matroids. So if I take a simple rank R, real representable matroids, the average flat size is bounded above by a constant depending only on R. And if you go into the machinery of our proof, really the bottleneck, I mean, we've got all the upper bounding that we need. The only bottleneck is to actually count the flats. And you can do that. And the answer is as follows. So the number of flats in a rank R matroid is going to be in the order of n times n minus g2 up to n minus gk, where k is the largest value so that the matroid's not k degenerate. So k is maximum so that m is not k degenerate. So if you take a matroid, all matroids are R degenerate. If you go to the definition of R, it's like its rank's too small. So all matroids are R degenerate. But they're not 1 degenerate. So there's going to be some sweet spot. There's going to be some value k where they're not k degenerate, and then if I go after that, I am k degenerate. So you take that value k, and the number of flats is of this order of magnitude. I call this our theorem, but actually it really comes like it's a 1-paragraph proof based on Lund's theorem. Like Lund does really all of the work. So I think that this theorem, the first theorem, is really maybe the right generalization of the problem. So instead of thinking about what is the size of the, instead of average flat size, average plane size, you just look at the average overall flat. So maybe this is the right notion. There's certainly no, I mean, it's clean, right? There's no exceptions. It's just that's the result. Okay. So I've been talking about real configurations over the reals, but it turns out you can do everything over the complex numbers as well. So this goes back to a classical result. So Melchior's result was already known in the complex numbers. So there's a theorem due to Hirzebruch, which says that in a simple rank 3 complex representable matroid, the average line length is less than 4. You certainly can't just get 3. There is a configuration that has all lines of length 3. And unlike Melchior's theorem, Hirzebruch's theorem doesn't have an easy proof. This is actually a fairly significant result in algebraic geometry. It certainly wasn't stated in the language of matroid theory. I very much doubt Hirzebruch ever learned what a matroid was.
Is 4 optimal here?
Sorry?
Is 4 optimal in the Hirzebruch?
Interesting question. I'll come back to that.
Okay.
So I don't think so. Everything that I said generalizes to complex representability, and it's not in an interesting way. Like all of the things that we used for the reals, there are the same theorems in the literature for reals and complex. So you could just get the result for free. Having said that, proving the results for the complex numbers was harder, but we didn't do that. So there were things like, so Doe's theorem and Lund's theorem are proved in the complex numbers. And Beck originally proved his theorem in the reals, and then it was later extended to the complex numbers. So that all took a bit of work to generalize from reals to complex. But for us, it's just taking a different, we're just taking a tool out of a toolbox, and one of them says real and one says complex. So this bound here, I think, should look like this. So this is R choose 2 plus some term that goes to 0 as the number of points in the matroid becomes large. So I know examples where you get this kind of bound, and these are called Dowling geometries, which are very graph theoretic in nature. So sort of a graph-like structure underlying these examples, which is why you're getting R choose 2, is because of what you see in complete graphs. This theorem, or this conjecture, shouldn't be true in the reals, and I don't know what the right answer should be for the reals, but it wouldn't surprise me that if you go to the reals, whether you even, like, I don't even know how to beat linear bound, I think. Maybe I do. I have to think about that more. Over the reals, it's going to be a long way from R choose 2. Anyway, I don't know how to get good bounds get good lower bounds on this over the reals. But for the complex numbers, that bound, I'm guessing, should be R choose 2. And then back to this question that you just asked, is 4 best possible here? The best example I know has 3.58. And I found that by looking through a paper of Piotr Pecora and just doing a calculation based on what he wrote about line arrangement. So this is a line arrangement called Wyman's line arrangement. And if you dualize, you get 3.58 as being the answer. And I did email him and ask him if he knew anything better, and he doesn't, and I'm sucker for a cheap conjecture, so I'll just say that I think that's probably as bad as it gets. But the conjecture that I'm more interested in is the second one, which says that the average line length should be at most 3 plus some term that goes to 0 as n becomes large. So if that's true, then there is a configuration that's as bad as possible. Right? If the second thing is true, then there is a configuration that's as bad as possible. And I think it's going to be this. I suspect it's probably this Wyman's line arrangement, because it's a surprisingly big number. It's hard to get anywhere near that. And I don't know enough about algebraic geometry to see if there's any hope at all of squeezing something better out of Hirzebruch's techniques, but I strongly suspect there isn't. This you end up getting basically if you think about line arrangements if you think about matroids where every line has length exactly 3 or 4, I don't think there's anything in Hirzebruch's techniques that prevent the average getting arbitrarily close to 4. Like the techniques seem to be blind to 4-point lines. It just don't know. It just seems to not know about 4-point lines. It knows about bigger lines and smaller lines, but there's no term in there that seems the coefficient of the terms that depend on 4-point lines is 0, and so it seems that it doesn't like 4-point lines. So you're not going to be able to say anything about what happens in that case, I think. Okay, so finally, let me just conclude by stating what I think the right answer is for average plane size. I don't know enough configurations to guess what the upper bound should be, but I think there should be an upper bound of the form 6 plus something that goes to 0 in n. And I also don't know what the right answer should be for the reals. So for the reals, you can actually achieve 6. But I think that as n becomes large, probably your answer is going to be much closer to 4 than 6. But I wouldn't be brave enough to conjecture 4 plus little o of 1. I just haven't. I don't think I've hit upon the right examples or analyzed the examples well enough over the reals to give you a meaningful upper bound. But for the complex numbers, I think the right answer should be 6 plus a bit, depending on the size of n. Okay, I'll stop there. Thanks very much.